so what we are going to see, yes?
I logged in with the word
Hmm?
I logged in with the word wait.
Oh, that's fine. I don't mind. Okay. Yeah, because that was the last class slide and I couldn't close. I couldn't show. All right. So today we'll do the other representation of Markov logic, which is to use it as view Markov logic as a template for Markov networks. And if time permit, we'll go into the inference. Maybe we'll cover some half of inference and the other half will be next class. Okay, so let's recall what was the Markov logic. So one view was, it is just the first of the formula with weight. Okay, so we see that MLN is just weighted first of the formula. And when we say ground, it means there's no variables. And we talked about Habermas universe, Habermas interpretation before. One thing that we need here is to define the probability. We have to assume that the underlying Habermas universe is actually finite. In fact, this kind of thing can be actually lifted. There are actually versions of Markov logic that allows infinite universe, but that's, we are not going to go over that kind of materials. Okay. Now, the weight of the interpretation is defined to be exponentiated weighted sum. Okay, and let's actually go back to the example that we had. So here we had two formulas. Smoke causes cancer, and friends are likely to influence smoking behavior. And if you have two constants, two object constants A and B, then we can ground this formula, and that gives us 6 ground formulas. Okay, and so there are actually many interpretations possible. So 2 to the power of 6 interpretations are possible. But among them is actually this guy. So everybody is friend to each other, and B is a smoker, but A is not, and both of them do not have cancer. So how likely is this state? So in order to find this, we have to find the weight of this interpretation. So for that, we have to go back to the idea of satisfaction. So does this interpretation satisfy the first rule? First rule in the first ground rules.
Yes.
Yes. Second one. Oops. So this is satisfied. This is not. This is
Yes.
satisfied because smoke A is false. So false if and only if it's false, right? What about this?
Yes.
Yes. What about this?
False.
Friends AB is true, but smokes A is false and smokes B is true. So this is true implies false if and only if true. So this is false. And the same way, this is false. So there are, among the 6 rules, there are only 3 rules that are true. And the rule also has different weight. So how can you find the weight here? So this is e to the power of 1.5 from the first one, and 1.1 from the third, and 1.1 from the fourth. Okay, so this is the weight of this interpretation. And this is only one of the 64. You can go over all the other interpretations and sum up. That gives us the partition function or the normalization factor that is C. Okay? Are we together? Okay. So that's it. Let's actually do one more exercises. Okay? So here I changed this to be the, so now, so for some reason I said A is a friend to B, but B doesn't feel A is a friend. And cancer, B is true, but smoke B is false. Okay, and both of, so A is not a doesn't have cancer, and A is also not a smoker. Now what is the weight of this interpretation? So, okay, what is the weight of this interpretation? Okay, so we have to check whether this interpretation satisfies each of the formula. So let's go to the first one. Does it satisfy?
Yes.
Yes. satisfy the second. Well, let's say so. This is true because it's what false if implies false, right? What about the second one?
Yes.
Yes. What about the next one?
Yes.
What about the next one?
Yes.
What about the next one?
Yes.
Smoke A is false, and smoke B is also false. False if and only if false is true.
Yes. Last one is false.
Hmm? What?
No.
Last one is also true. Okay? Alright, so this is actually most likely state because every rule is actually true. So this is, okay, this is not easy. Okay. Every tool has certain weakness. So this one satisfies all of them. So this is 1.5 times 2 plus, oops. So e to the power of 3 plus 4.4. Because that's the sum of the all the weight. Now, if you look at this, it's a bit weird actually if you think about it. This is highly likely the case, but B is not a smoker, but B still have a cancer. Okay, so I'm not going into the some weirdness in this language, but that's actually the next topic. When we go into LPMLN, I'm going to revisit this example and see there's actually certain weird thing going on with this example. Okay, so semantically there is something going on here, but let me just stick to the current definition. Okay. All right. So that is actually the view that we had, and now we will look at the view in terms of Markov networks. So this is actually combining the logic and probability. So the previous view that I introduced is more close to the logical point of view. Now the second view is more close to the graphical models point of view. Okay. So this is actually the slide that you saw before. So we represent this domain. It's similar to the example that we just talked about in terms of log linear model. And I said that you can define, so when you write log linear model, you have the exponent of this function is a linear function. So it's the sum of over this wi times fix. Now this feature is, we assume this is Boolean, so it's either 1 or 0. But how do you define feature? When this feature becomes 1? And what is this feature becoming 1 means? That can be up to you. And if you do some way like this, so you can say that this feature is expressed as 1 if smoking is false or cancer is true. Okay, so then in that case, this feature expresses, so it's 1. Otherwise, the feature is return 0. Okay, so that is one way to write the Markov networks. And what we do in Markov logic is to take this view. So we'll define features in terms of the formulas. Okay, so how do we do? So we are given a Markov logic, which is just a set of first formulas, and then we also say what is the Hobron universe, the set of object constants to denote individuals. Okay, now Markov networks is just a graph. It has a node and edges. So each node is actually ground atom in the logic. Okay, and each feature each feature is actually associated with the each ground formula. Okay, so let's actually look at. Okay, let me just go into this, and I'll show the example in the next slide. Okay, so I didn't actually define clearly yet. So this is actually the idea. So when you do the weighted sum, okay, so weight of formula. So in Markov logic, you have the weight of the formula. So this that weight is actually the weight in the Markov networks. Okay, And the feature is now, we will use NIX to denote the feature. And what is this feature? This feature is number of ground formulas that is coming from the I rule, or I formula, that are true in X. Okay, so this is actually lengthy description, so let me actually repeat. So in Markov logic, you have W, okay. You have Wi, Fi, okay? So Wi is a weight, which is some real number, and Fi is a formula. Now this Fi is non-ground formula, okay? So when Markov, so when you turn this Markov logic into Markov networks, what happens is each of these non-ground formula is considered in this weighted sum, okay? This weight is actually the weight here that you write, and in this case, you look at the number of ground formulas that come from Fix. So if you replace the variable x with all ground instances, then it will generate multiple ground formulas, right? How many of them are true? The number of ground formulas that are true, that is the feature here. Okay? So
we just use the number.
yeah, let me actually go through the example to illustrate this idea, and then we'll come back to this definition to see. So now I'm going to draw the Markov networks. Okay? So before we are giving the ground formulas, but now let's look at Markov networks. So there are two object constants, Anna and Bob. Okay? So I said each ground atom is a node in the Markov networks. Okay? So from the first one, we have smokes A and cancer A, smokes B, cancer B. Though these are the nodes, right? From the second one, we have friends AB, friends AA, AB, BA, BB, right? So this is actually all ground atoms in the Markov networks, right? Are we done? Okay. So here we wrote all the ground, we consider all the ground atoms. Basically the, yeah, so, yeah. It's called Hobrand base, but I didn't introduce that term, so let me not go into that. So this is just a ground atom. Now we have to connect this node. The way that we do is each, look at the formula, okay? And the formula may contain multiple atoms. Connect them with the edge, okay? So for instance, if you have smokes X implies cancer X, from this you can actually draw two edges, okay? So what could that be?
Smoke A, cancer A.
Yeah, so smoke and cancer are related, right? Okay, smokes A implies cancer A is one of the ground rules, right? So from that rule, we know that these two atoms occur in the same formula. So just connect those. Okay? Same way, you have smoke B and cancer B, right? That's it. So from the first rule, if the ground atoms occur in the same formula, just draw the edge between them. And this gives the clique. Okay? Remember what we did in the Markov networks is to assign the potential function to the clique. And this is the clique that is that we consider in Markov logic. Okay? All right, then the next one is this. So let's say smokes, friends, what should we do? Let's actually look at x equals A and y equals B. Okay? So then which one are connected to each other? These three, right? Friends AB implies smokes A if and only if smoke B. So these three atoms participate in the same formula. So we draw edge between them. So this is another clique, and whose value, potential function will have this value 1.1. It's not exactly 1.1, but its weight will be 1.1. Okay? Similarly, if you have friends BA, then you have this, right? Also, it might be a bit unintuitive, but X and Y can be same. So friends AA implies smoke A, smoke A. So that means you can actually draw this edge, right? Are we together? Same way, friends BB implies smokes B if and only if smokes B. So this is it. Okay, so when you write this thing, okay, you can now understand what potential function that we are going to consider for the clique. So we look at this clique. I don't know whether I can change the color. Let's actually not bother some. So this is one clique. This is another clique. This is another clique. This is another clique. Another clique. Another clique. So we have this. Was this 6? Yeah, we have 6 cliques here. Okay. Are we together? So then it's just a Markov networks. Okay. Okay, so let's see how this idea works. So this is the same example, and note here that the function is now written in terms, probability is written in this form, where this Wi is the weight of the formula here, and Nix is how many ground formulas are true from the ith formula. Okay? So with that in mind, let's try to find out the P of X. So here I give these things. So I denoted what are the what is the truth value of each atom. So it's actually the same as what you saw before. AB is everybody is friends to each other, and B is the only smoker. Okay, so this X is an interpretation where friends it's not actually that easy to write. BA, and how can one write? Okay, and smokes B. Okay, so this is the interpretation, same interpretation that you saw before. So now let's actually look at the P of X here. You know what? Let me just write on the board. Okay. So P of X. Okay, so this is a big number, so I'm not going to compute this. But let's look at the thing. So this is actually the weight that we added up before, but it's actually that slightly different way. So we look at the first one. Okay, so W1 is 1.5, right? Okay, so it's 1.5. And I have to multiply this with the number of ground formulas that come from the first rule that are true under this interpretation. So how many ground rules are coming from the first rule? 2. Smokes A implies cancer A, smoke B implies cancer B. How many of them are true under the current interpretation? 1. Okay, so that gives me 1 plus. Now W2. Okay, so when I equals 2, W2 is 1.1. And I have to count how many ground formulas from the second rule is true under this interpretation. How many are true?
3.
3?
Oh.
No, we did the same thing before.
Yeah.
That's actually 2. Okay. This is the exact same result. It's just a different way to calculate. Okay. If you are confused, you can go back and check. This is the same thing. All right. Okay. So let's do another exercise. Okay, so this is the second interpretation that I showed you before. Okay. Now with this one, friends BA is no longer true, and smokes B is no longer true, but cancer B is true. Okay, so remember the second interpretation. So we are going to do the same thing, but now what changes here is this guy, right? Okay, so formula 1. How many ground instances are true? 2, right? Smokes A implies cancer A is actually true. Smokes B implies cancer B is also true under this interpretation. So it's actually 2. What about the second one? How many ground formulas from the second rule are true? 4. So this is it. And of course, it's actually the same result. Yes? Yeah, this is a sum. Okay, so the sum here was for Wi and I, right? And there are only 2 formulas here, which means that I have W1 times N1x plus W2 times N2x. That's what I show you here.
I was asking what is that summation of values?
Are you talking about this?
Z.
Oh, Z. Yeah. So Z is the sum of all interpretations. I mean, all the weight that we do. So this is just one of them, but you can do the others. Okay. There are actually 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. 2 to the power 8 interpretations that you have, and I don't have time to write everything here. And that's actually an interesting thing that probability computation is actually not that simple. I am only writing the numerator, okay? But for writing the denominator, I have to sum up all such weight of each interpretation. And that's actually exponential, okay? So we'll actually go into that thing later. When we do the probability computation, we cannot really generate all possible interpretations and compute their weight. That's infeasible to do most of the time. So what we do is to use the sampling. Okay, so you'll see later how do we do the sampling method. Use the sampling to find this z value. Okay. All right. So that's it. Okay, so we'll look at the inference. How are we doing on time? Oh, actually good. All right. So for the inference, in logical formalism, we used DPLL-like algorithm to find exact assignment that makes all things true. But I just said it's infeasible to do that in the probabilistic setting. So inference here is actually a bit different. What we do is to use the standard method that was developed in the machine learning community, okay, with probabilistic graphical models. So there are 2 types of inference most of the time. One is actually finding the most probable state. Okay, so this is also called map inference, maximum posterior. So finding the most likely state of the world consistent with some evidence. That's the one type of the inference. Now, to do this first one, you don't actually need to know the probability. You don't need to know the z values. As long as the weight is the maximum, then you're done. Okay. The second one is actually more difficult. You have to compute the conditional probabilities. Okay. And for that, you need to know the partition function or the normalization factor, which is very costly in most of the time. Okay. Now, what I just said is probably too simplified thing. So, of course, in principle, you can use the Markov network's inference to compute Markov logic, but there are actually more. When the size becomes bigger and bigger, then that method also suffers. So people have found out that actually there is a better way to compute this using using the combination of both logical inference and the probabilistic inference. Okay, So that's actually more advanced inference method that exploits the logical inference feature. Okay. All right. So we'll talk about each of these two inference. The first one is map inference, and the problem is to find most likely state of the world given the evidence. In other words, you know certain atoms are true or false. Some subset of atoms are true or false. And you need to find out what is the interpretation that gives the most highest probability. Okay, what is the most likely situation given observing this evidence? You can formulate the problem with this way: argmax of y of probability of y given x. So what is this thing? So it's a conditional probability. We are given evidence x, and you want to know the probability of y being true. Now, we are not actually interested in the probability of y itself, but we are interested in what is the assignment of y to make this probability to be the maximum. That's what argmax is about. Its argument is actually maximized. The argument is to contribute to the maximum value. So it looks like a probability, but it turns out that we don't necessarily need to know the probability to find out the value of y. Okay, so let's see. Actually, let's think about to do this. So let's just unfold the definition. So if you have argmax y, okay, what is the probability of y given x? How do we write this? Okay, so this is by definition this is I, wi, and I'm going to use x as an observed variable. So when I write ni xy means the ground formula where x is already having this fixed value from the evidence. Okay. In the same way, I'm only looking at those interpretations where x assignment to x is consistent with the given one. Okay. So this is how you write. Okay. Are we together here? Okay. So just look at the interpretation where the assignment to x is consistent with this x. Okay, we only look at those interpretations. We add up only those formulas, only those formulas weight, and divide by the sum of all of them. Okay. So if we have this, what you will realize is actually this is actually constant. Okay, once you have the x. Assignment of x is fixed, this is constant. So you can forget about the y is not okay. I give up. So let me write here. So we can forget about the denominator, and we only look at the numerator part. But also, if you look at the numerator, there's an exponential function, but we can forget about that, and we can only look at the inside. Right? Because exponential function is monotonic function. So if the argument, your exponent, is actually maximal, then the exponential function is also maximal, and vice versa. So we don't need to worry about that. Then what we do here, we don't actually, so finding, this is actually y. So finding the value of y that maximizes this one is actually the same y that maximizes the probability, right? So we don't have to consider the complicated z and exponential function. We can just look at the linear function here, right? So this is the writing. And if you do that, this is actually just like a weighted max set problem, which I'm going to explain soon. So we know the satisfiability problem, which is given the set of clauses, you need to find the satisfying assignment. Okay. Now weighted set is some of the clauses will be, those clauses will have the weight, and you want to find the assignment that maximize those weight. Okay. So it's actually exactly the same problem here. Okay. So for instance, in the weighted set problem, you can say like 1 P or Q, 2 not P, and R, 3 Q or something like this. Okay. Now you have to find an assignment that satisfies all of them, but also you have to find an assignment that gives the sum of the weight to be the maximum. Okay. So if I satisfies these two, then this I will get the weight 5. If this I satisfies only these two, I will get the value 3. So which I is a better I? The first one. Okay, so in that sense, they can try to find the maximal, the interpretation that gives the maximal weight. Now in this case, you don't actually have to satisfy all the formulas as well. So this is exactly the same problem as Markov logic. In Markov logic, there's actually more to this when you go into the probability. But as long as you look at the map inference, then the problem comes back to this weighted set problem. Okay. So one of the well-known solver is MaxWalkSAT solver, and we'll look at the algorithm now. Before we do that, we'll first need to look at the Workset algorithm, where the MaxWalkSAT comes from. MaxWalkSAT is actually the modification of this algorithm. Okay? All right, so let's look at this algorithm together, and we will do the exercise or example. First, we already know one way to find the satisfying assignment. That was DPLL, right? In DPLL, the interpretation that you found satisfy all the clauses. Okay. Now in the Workset, this is not necessarily so. Okay. Or actually, let's say this way. DPLL is a deterministic algorithm. Okay, so you can, if there is a solution, you can always find. But this algorithm that we are going to look at now is the stochastic algorithm, which means if you're lucky, you'll find solution pretty quickly. But if you're unlucky, then you may not be able to find some solution. Okay. All right. It turns out that this algorithm is quite simple. Okay, it's actually simpler than the DPLL, and sometimes it works actually better if you know that finding the solution that satisfies all constraints is infeasible, then this Workset algorithm works better in that case. On the other hand, of course, if you want to do some formal verification, this kind of stochastic algorithm does not work, because you may be just unlucky to find the violation of some critical failure. So the one that we evaluate here is the number of satisfied clauses. If the number of satisfied clauses is actually the every clause, then this is of course the solution that is also generated by DPLL. Okay, but here it may not find all solution. It may not find an interpretation that satisfies all clauses. Now, how do we go? So the first one, so first, just randomly assign the truth values to atoms. Okay, so input is actually the clauses, same as DPLL, and you have to find an interpretation that satisfies all clauses, or most clauses. So first, you initialize the interpretation to be arbitrary thing. Okay, and then you repeat this from j equals 1 to max flips. If your solution, current solution that you have, satisfy all clauses, then there's nothing further that you can do. You just return the solution. This is the happiest time. You randomly guessed, and the guess is correct. Okay, if satisfy all solutions or all clauses, then you're done. But most of the time, it will fall into this case below. So some clauses may not be true. In that case, randomly select some clause that is false under the current interpretation and call that clause C. Okay, pick one clause that is currently false. Okay, and with probability P, you do one of these two. Okay, one thing is if this P, if in the first case is you flip one of the variables in C randomly. Okay, or you do the other thing. Find the variable in C that maximizes the number of satisfied clauses. Okay, so let's look at the example. To be on the safe side, let me write the board. So we are given this clause. Okay. Okay. So let's assume P, Q, R is true, false, false. Okay? Are we together? Okay, so this is just a random truth assignment. Okay, so let's go. So, does this interpretation satisfy the first clause?
No.
No. Second?
No.
Third?
No.
Fourth?
Yes.
Okay. So there are three clauses that are currently false. Actually, let's check. This is false or false. So this is it. False or false. Okay. False or false. Yes. And not Q is true. So that is. So this one is the only one that is satisfied. Good. Now we have to randomly select some clause. Okay. So let's actually see. So these are three possibilities. So you have to do random selection. Let's actually choose this guy. Okay. So Q or R. Okay. And so that's our current C, the clause C that we selected. Okay. And with probability P, we can do these two things. Okay. So let's assume that we are in the second case. Okay. So you can set the probability P in some way. So let's say 0.5, and you flip the coin, and if it is head, you do the first. If it is tail, you do the second. So it turns out to be the tail. So we'll do the second one, because that's actually more difficult to see. So what we have to do is we have to look at the current variable in C that maximizes the number of clauses when you flip it. Okay? So let's consider two possibilities. If we flip Q, that will be the 1, 1, 0. If we flip R, that will be 1, 0, 1. So each of them is coming from the current one, right? So current one is 1, 0, 0. If you flip Q, then it's 1, 1, 0. If you flip R, it will be 1, 0, 1. Are we together? Okay. So we have to choose among these two interpretations that maximize the number of satisfied clauses. Okay, so let's check this. If it is 1, 1, 0, is it true?
Yes. Yes.
Is it true?
No.
Is it true?
Yes.
Is it true?
No.
Okay. So the number of satisfied clauses is actually 2 here. Let's go to this one. 1, 0, 1.
False.
1, 0, 1. This is false or false, so this is false.
True.
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 True,
True.
true. Okay? So which one should we select?
R.
R, because R gives the more number of clauses to be chosen. So we will forget about this and we'll select this as our current solution. Okay? And then we repeat. Okay? So let's go back. So now we have to find again whether this current solution satisfies all clauses. Is it? Of course not. Right? The first one is not satisfied. So then we have to randomly select the clauses that is not satisfied. There's only one unsatisfied clauses, so there's no randomness here. So we have to select this one. Okay? And then you flip the coin, and it turns out that this is head now. Okay? So what shall we do? We have to select random thing here, right? And turns out that if we are lucky, let's just flip P. Then we will get 0, 0, 1, right? And then repeat. Does this satisfy the first clause?
Yes.
Yes. Second clause?
Yes.
Yes. Third clause?
Yes.
Fourth clause?
Yes.
Yes. So we are done. So unlike DPLM, we are very lucky because I didn't manipulate the example in some sense. So only just 3 iterations you can find the solution here. There's actually some reason for this thing. So this is kind of greedy search. You try to maximize the number of clauses. It doesn't necessarily mean that you will find the best. You will find the solution that satisfies all of them. But you try to maximize those local part. It turns out that you are lucky. If you're lucky, then you can get the solution.
Sorry, I didn't get. When do we randomly flip and when do we actually see that it maximizes the number of
Which line are you talking about?
with the width line and the else line? Like
C, randomly selected clauses as defaulting solution. Are you talking about that?
There are times when we randomly flip a variable and there are other times when we flip to maximize
This line. Okay. So this line is random.
the line after that.
This line is just randomly select. So that if there are 3 random clauses, 3 clauses that are not true, then you randomly select one of them, right? This thing is the current clause. This is clause. So for instance, we have Q or R.
Yeah.
There's a clause. It has 2 atoms, okay? And choose one of them randomly and flip its value. So if Q was here 0 and 0, right? You select Q and flip it, then it becomes 1. And other variables are the same.
I don't understand when do we randomly flip and when do we flip to maximize? Like,
Oh, that's the probability. So I said before, with probability P, meaning that you have certain fixed probability in mind. This is a parameter that you give before calling the algorithm. So let's say 0.5. If it is head, then do the first one. Flip randomly selected variables in C. If it is tail, then do the here.
Why do you do that? I mean, it makes more sense to do the second one.
It's not necessarily the case. If you only try to do that, this is a greedy search. So you will not get into the global maximum. Okay, so you have to sometimes do the something weird. Okay. So you can think about it. If you do the climbing on the hill and if you try to reach to that only, you kind of stuck there. So you cannot actually find a better solution if you do that. So that's a random list there. Yes?
So over the time, do we maintain the base solution that we found and return that at the end?
Can you say again?
So basically, if we don't find a solution by the max least number of times, then
that's actually interesting. So that's actually my next slide, I believe. So you do all these iterations. So max flip was done. Okay. Okay. So what is the thing? Let's actually do Socrates. Okay. So let me just open it now. This one is multi-choice, so you can use this one. Okay, So let's see. The question is, if the Workset algorithm returns failure after it tries max flip times, it exhausts all the things, what can we conclude? Okay, are we done? All right, so let's look at the answer. Okay, what is E? Okay, I don't know. Nobody selected C. Okay, fine. The answer is actually B. Okay, and some people say yes. Let's see. Yes. So, I mean, it's actually obvious to see if you look at the algorithm. If your max flip is too small, then you don't actually have chances to reach to the maximum, right? So that doesn't necessarily mean that the sentence is unsatisfiable. You're just unlucky. You didn't try hard. Okay, you didn't walk too much to go into the peak of the mountain. Okay, so you can actually say nothing. Of course, if you happen to find a solution within the max flip, then of course the sentence is definitely satisfiable because you found one example. Okay, so this algorithm is actually very difficult to say. When it fails, you cannot really conclude anything. There is no solution possible. Unlike DPLL, where you exhaust all the search and you can prove that there is no solution. So like the homework problem that you did, it uses something like that algorithm, so that when you do the entailment checking, okay, the query checking, there was no stable model, unsatisfiable, meaning that the entailment is always true. That kind of reasoning cannot be done with a Workset. On the other hand, of course, it has different application, like the map inference that we do. Okay. Right, I didn't introduce MaxWalkSAT, but the algorithm actually is very similar. The only difference is what we want to maximize. Okay, so in the Workset algorithm, what we wanted to maximize was the number of clauses, but now it's the number of ways that we want to maximize. Okay. Let's actually play with that. Okay, so maybe we can try to use the same example. Let's actually give the weight to each of the clauses. So this is 1, 2, 3, 4. Okay, I cannot find a better marker. All right. So let me just write. This is weight 1, this is weight 2, weight 3, weight 4. Okay? And let's say the threshold is 10. Okay? So the threshold equals 10. So that means we have to satisfy all clauses. Okay? You can set threshold to be lower than that, that's also fine. But for this example, let's say 10. Okay? So the same way, but now we are changing the we changed the evaluation function. So initially PQR is 1, 0, 0. Okay. So what is the number of ways of the satisfied clauses? 4. Okay. So yeah. So look at this one. Now instead of this, I can see. So weight of the satisfied clauses. We are not counting the clause now. We are actually getting the weight of that satisfied clause. So this is actually 4, right? So currently we are satisfying all the clauses with weight 4. And Now we go into, so we check the if clauses, right? So is this greater than 10? No. So then we cannot return the solution. We go into the next thing. C, randomly select clauses that is false in the solution. So it's the same as before. We already checked this. So here, these are the false clauses. We select randomly, but let's just choose the same randomness, which we select this one as C. Okay? With probability P, we flip, we do one of these things. But let's actually choose the second bridge as if it was a tail. So flip which variable in C that maximizes the weighted number of set of clauses. Now we actually considered these two before, right? Okay, so if we have this guy, then what is the sum of the weight? That's 1 plus 3, which is 4. If you flip it, you actually don't improve, right? What about 1, 0, 1? That's, these guys are true, so 2 plus 3 plus 4, which is 9. This is better. So we don't choose this guy, same as before, we only choose this one. Okay, so we are flipping the R, not the flipping the Q. Okay, so then we go back to this and check whether 9 is greater than 10. But 9 is still not greater than 10. So we have to come back to here to select random clauses that is false. And that is actually only this one, the same as before, right? And let's pretend that we flip randomly, but let's flip P, okay? So then we get this, right? So if we do that, what is the sum of the weight? That is 10. And when you do the upper part, okay, 10 is greater than or equal to 10, so we return the solution. If we set the threshold to be 9, we could have finished it here, which is suboptimal. Okay, it is actually not very bad because we are only losing 1 from the sum of the weight. Okay, so you can actually change this threshold. If you don't even bother with this, you can be satisfied with these things. Okay, are we together? Yes.
I guess, greater than you were saying greater than equal to threshold.
Hmm?
By greater than you were saying greater than equal to threshold.
Oh yeah, okay, I forgot. I mean, that doesn't matter. Yeah, okay. You can change to greater than or greater. But yeah, to be precise, yes. I meant when I do this illustration, I had in mind this was greater than equal. Okay. All right. Any other question? All right, so I guess that's the perfect time to finish. The next thing is the other half of the inference, which is how to compute the probability. Okay, and then we'll actually try to use the alchemy system that actually does this computation for you. So you don't have to do this manually all the time. Okay, so let me stop here and let me open the Socrative.